We're going to look now at a technique that will streamline matters for us in taking the derivative of a function. Consider this function, it is a binomial cubed. Now, there are at least two ways that we can identify right now to attack the derivative of this problem. We could just stretch this out a little bit and say we have three factors of the binomial and use the product rule. Another way would be to stretch out like this and then expand the whole thing. That is, multiply the binomials out and then deal with the polynomial that results. Either of those techniques involves quite a bit of manipulation. There's another way for us to deal with this, and here's that way. This is called the chain rule. The chain rule. If f of x is this, then we can let a variable stand in for this binomial. Let a single letter stand in for this. Now, we're going to do a lot of this mentally a little bit later, but for right now, we're going to actually write the letter and let it stand in and see what happens. We're going to let a letter like u stand in for 2x minus 5, and now the function can be written as u cubed. And it turns out that the derivative of the function is the derivative of f in terms of u. That is, the derivative of this times the derivative of this expression. It's u prime, which is the derivative of 2x minus 5. It's kind of like we're putting a function into a function. We're sort of creating a composite situation. Now, the way it works is like this, and it goes rather fast. And I know this is rather confusing at this point, but it'll all be clear in just a minute. If we're thinking about the derivative of this, then it's 3u squared. And then the derivative of the u part, now the u part was just what was in parentheses here. The derivative of this is just 2. Now, the u, remember, turned out to be the 2x minus 5, and when we pop that back into the situation, we have 6 times binomial squared. And now this technique makes it a lot faster to deal with the derivative. But using the technique, we have to use our imagination a little bit and put this u letter into the situation. Incidentally, the name chain rule comes from this idea. What we're really doing here in this product situation is we're taking a dy, the derivative of y with respect to u, and multiplying times that u prime is really just the derivative of u with respect to x. You see, now look at the flow here. It's derivative of u with respect to, the derivative of y with respect of u, derivative of u with respect to x. And now with this chain involved, this really is derivative of y with respect to x. So that's kind of conceptually how it's going. Well, let's go through it another time or two. Here's another problem. This one is a quotient. If we were doing this particular problem using the rules that we talked about earlier, that is, using the quotient rule, it would look like this. And incidentally, the chain rule doesn't always represent a saving of time. It's just about the same amount of time that it would take doing this by the old method as with the chain rule. I just want to show you both techniques. If we're using the quotient rule, then remember it is the derivative is the denominator times the derivative of the numerator, the derivative of 2, and then minus the numerator times the derivative of the denominator. The derivative of 3x plus 1 is 3. And then all of this is over the denominator squared. Now, cleaning up a little bit, the 0 takes this term out, so we have negative 6 over denominator squared, or 3x plus 1 squared. That's easy enough. But if we use the chain rule, it looks like this. Now, we're going through this very slowly and meticulously. I'll show you how to deal with it much faster in just a minute. But we take our function and then we make a replacement, either mentally or actually show that replacement. And I'm showing it here. We're thinking of the 3x plus 1, you see, as being replaced with a single letter. So now our expression looks like 2 over u. And now we're thinking of this, manipulate this a little bit, throw the u into the numerator, and we have 2u to the negative 1. Okay, our derivative is the derivative of this, you see, with respect to the u, and then it's u prime. It is, u prime. This is the u, and so it's u prime. So it's f prime of u, which is the derivative of this. So it's negative 1 times 2, that's negative 2u to the negative 2. And then the u prime is the derivative of this, which is 3. And now let the smoke clear on this, and we have, let's see, negative 2 times 3 is negative 6, and the u to the negative 2 kicks that downstairs, and the u was the binomial 3x plus 1, so 3x plus 1 squared, as we found earlier. Now we're going to pop back to this problem in just a minute. I want to show you one more and go through this u process. This one involves a radical, and the radicand is the u part here. So we're talking about g of x is the square root of u. We could say this is g of u if we make the substitution back the other way, but at any rate, it is the square root of u, or u to the 1/2 power. Now, the derivative is the derivative of this times the derivative of that. You see, it is g prime of u, which is the derivative of that, and then u prime, which is the derivative of this. This is u, so u prime would be the derivative of that. So we have, let's see, the derivative of this is 1/2 u to the negative 1/2. Now remember, subtracting 1 here, 1/2 minus 1 is negative 1/2. That's why this negative 1/2 is here. And then the u prime means, let's see, the derivative of this is negative 2. That's where that comes from. Multiplying here, the 2's cancel, and we have negative u to the negative 1/2. So that is 1 over u to the 1/2, or 1 over the square root of u. But u is that binomial, 3 minus 2x. And when we plug that back in, we're finished with the problem. Now, the way we'll actually work through these problems is like this. We're not going to go through and think actively every time about replacing the u and writing the u in and so forth. We're just going to think about it. And here's how the thought process works. All right, just think of this. I'm just going to rewrite this for convenience as 3 minus 2x to the 1/2 power. That's kind of helpful. All right, now I'm just thinking of a single entity here. Think of single entity. Here's our u from before, but just think single entity. All right, if we're letting think of one unit or one idea, one letter stand in for this, then think about the derivative as, take the derivative in terms of this single entity. So it's 1/2 times single entity to an exponent which is 1 less than this. Okay, so 1/2 times single entity times an exponent which is 1 less than this. Now, multiply that times the derivative of the single entity. You see, that's all you're kind of doing it as though this were a single letter, and then take the derivative of that which was replaced by the single letter. So we have negative 2 here. And then cleaning up, we're done. So let's see. This kicks down into the denominator. The 1/2 times the negative 2 is negative 1. So that gives us a negative 1 in the numerator. And in the denominator, we have this binomial to the 1/2 power, or the square root of that binomial. You see, thinking in terms of this single entity idea gives us a fast track through the problem. Let's work back this way and work this one in terms of that single entity idea. So here, we might do something like this. And there are several ways of doing these correctly. If we think of this, for example, as, I'm just going to kick this binomial to the numerator by doing that. And now I'm thinking of this as the single entity. And taking the derivative of this as a single entity, single variable, you see, it's minus 1 times 2, that's minus 2, times the single entity to an exponent 1 less than this. So f prime of x then, starting it out, negative 1 times 2, negative 2, times the single entity to an exponent 1 less than that. Now, follow that by a factor which is the derivative of the single entity. So we have times 3. And now we just clean up, and we're finished. Let's see, negative 2 times 3 is negative 6, so it'll be negative 6 in the numerator. And the denominator is the 3x plus 1 squared. And so we've accomplished the situation in much less time than we could have otherwise. Sometimes the chain rule can be used as a nested situation within a more complicated problem. Here's an example. F of x is this, and we want to find its derivative. We're thinking of the 3x minus 9 as that single entity that we've been referring to. Whether we write it down or not is really beside the point. But the derivative now of the function, we're thinking in terms of using the product rule, so it's x times the derivative of this. And in taking the derivative of this part, we're using the chain rule. So I've written in here, for emphasis, x times, use the chain rule here, and then plus, it's this other factor times the derivative of x. So it's 3x minus 9 cubed, the derivative of x is 1. Now, all of this other part out here is kind of outside clutter when you're trying to concentrate on the chain rule. So it's just a matter of bringing down, manipulating, and so forth. Let's concentrate here on using the chain rule to derive or to find the derivative of this part of the problem. So we have single entity cubed. So it's 3 times the derivative of that as a single entity is 3 times single entity squared. And then multiply that times the derivative of the single entity. So we have 3 times binomial squared times the derivative of the binomial is this. Now it's a matter of cleaning up, and there's a lot of work to do in cleaning up on this problem. We have 3 times 3, 9 times x, 9x, and I brought down this part, and then over here I've just brought down this. Now your teacher may say, well, it's okay to leave the problem like this. We're just concentrating on how to use the chain rule and the technique for that, and we've accomplished that at this point in the problem. Other teachers might say, well, you need the practice in the algebra manipulation, so we need to take this a bit further and simplify it a little bit. You see, there's a lot of simplifying to do. We have a binomial squared, same binomial cubed over here. That gives us a factoring opportunity. We have common factors in both of the binomials. That gives us another kind of opportunity. Let me show a manipulation here. I'm going to manipulate this a little bit because a lot of times when you come to some kind of conclusion on your paper, you might turn to the back of the book and look to see if you've worked the problem correctly. And there's something that looks entirely different in the back of the book. Well, a lot of times that entirely different looking thing in the back of the book turns out to be the same thing that you got. So you're not necessarily wrong, it's just not manipulated into the same form. That's all there is to it. So let me show you a little manipulation here, and you probably know this. You can skip over this if you want to, but it's just a real fast idea. Now, I'm looking at these two terms, and I'm taking out the common factor of 3x minus 9 squared. So if I take 3x minus 9 squared out of this term, I'm left with 9x. Out of this term, I'm left with 3x minus 9. Now, collecting here, I get 12x minus 9. But I have these common factors in both of the binomials. I'd like to snag the 3 out of here and a 3 out of there. And when I take the 3 out of here, I have 3 times x minus 3 all squared. I take the 3 out of here, and I have 3 times 4x minus 3. Now I've written that up here. So 3 times x minus 3 all squared, and then 3 times 4x minus 3. Okay, squaring the 3, I get 9. Squaring the binomial, I get the binomial squared. I'll bring down the 3 in this other factor. And then expanding a little further or multiplying the constants, 9 times 3, 27, times x minus 3 squared times this other factor. Anyway, a lot of manipulation. Let's take a look at another one. We have a binomial, looks kind of complicated, squared. And again, we're going to use the chain rule within the process of finding the derivative here. So y prime then is, well, let's see. Our idea is to use the chain rule notion from the get-go. We're thinking of this as our single entity. So we take the derivative in terms of the single entity. Well, let's see, it's a single entity squared, so it's 2 times single entity to the first power. 2 times single entity to the first power times the derivative of that. So it's times the derivative of that piece. Now, all right, let's turn our attention to that part of it. And incidentally, right here, I'm just multiplying 2 times the numerator, so we have this. And I've left this in factored form anyway. All right, so the derivative here, now here's where we're using the quotient rule. So we take the denominator and multiply times the derivative of the numerator. So it's denominator times derivative of the numerator. Then minus the numerator times the derivative of the denominator. The derivative of this is 2x. And then all of this is over the denominator squared. And now it's, again, it's just a matter of cleaning up. And if we, let's see, I've taken this factor in this numerator and just brought it down. And I've expanded this and collected some terms. So it was 3 times x squared plus 3, and then minus this product. And when you collect like terms and so forth, you get this trinomial. And then in the denominator, it's x squared plus 3 times x squared plus 3 squared. So we have 3 factors of that binomial in our denominator. There may be some other manipulation opportunities if you'd like to take advantage of them.